It's always lovely to be here. Three signs here at Wrocław RB. Oh, can I move the microphone a little? Is that okay? Okay. So three signs here at Wrocław RB. You've had way too much coffee, not enough sleep, and your voice, you can hear it's been 2 days of partying. So I apologize. I may not be the speaker you deserve, but it's the one that you're going to get. All right. I see the presentation is working. Let's just get into it. Functional programming. So, I'm sure you've all heard of functional programming, and I'm sure you've been told that it's about programming with pure functions and without side effects, right? Hands up. Agreed? Disagree? I'm going to need more from you guys. I need the energy in this room to go up because it's only going to get weird. Trust me. This is not true. This is the worst possible explanation of what functional programming is, and I'm here to set the record straight. So we're going to learn 3 terms. We're going to learn 2 visualization techniques, 1 programming concept, and we're going to learn absolutely nothing about monads. This is not that talk. Because I'm here to teach you functional programming, not monad programming. So, meet Mr. Chang. He's your classic community college professor with a sombrero, feet up in the air, just chilling. When this slide is up, I want you to relax, lean back, breathe, think about what you've just seen, and sort of process it. But that also means that when he is not up, I need you to put your phone down, lean forward, and read between the lines, because I am not here to teach you a bunch of buzzwords. I want you to take every single slide you see and think about how it applies to your existing code base. And I promise you, if you put in the effort today, you will wake up tomorrow a better Ruby developer. This is my promise to you, okay? Sounds good? I'm gonna need more. Thank you. Let's start with some softballs. Now, I'm going to try to not ask any rhetorical questions or trick questions. This is not an interview. So, if I ask something and it seems obvious, I want you to answer anyway. Just shout it out, because this is going to help you process this information. We're looking at something up on the screen. Can you take a wild guess what kind of application we're dealing with here? Yeah, some kind of shopping cart, e-commerce. I think that would be a reasonable assumption. Can you tell me how many books are in this shopping cart? 3 books. Can you tell me if any of them are on sale? 1, which one? The last one. So the first 2 books, that's from yesterday's lightning talk. The last book, I threw it in there because it's a book I read recently, like maybe half a year ago. It's about women in computing, in the beginning of the computing field, and it turns out that there's a lot of interesting anecdotes, and I think not enough people learn about our own history as a computer science field, so I highly recommend it. So, that's our first slide. Sorry? There was a typo? I'm sure there's more than one. Okay. So it's going to be here too because I just copy-pasted. So this is our second slide, and here I want to ask you, when was the Principles of Philosophy published? Louder. Okay, by whom? By Descartes. And how old is he when he published it? "48 years old, yes. So think about what's just happening here. I gave you 0 information, but you were able to not only figure out meaningful information that was here, you were actually able to do some graph traversals, even though I didn't tell you that those things are somehow joined together, right? So you've just learned what is data. Data is information at rest. It means that it's meaningful without needing a computer to run it. You are now a data engineer. The other interesting property about data, except for the fact that you don't need a computer to have any meaningful information processed from it, and in fact, new facts, right? Because there was nothing about how old Descartes was. This is something you figured out by joining other facts that were already there. The other interesting thing, sorry, first slide. Potter Stewart, if you don't know who that is a Supreme Court justice, and he famously, when asked what is pornography, said that I know it when I see it. And that's how I want you to remember what data is. Next time anyone asks you what is data, just smile and think, I know it when I see it. That's the first property of data. It's information at rest. It doesn't need a computer to be interpreted. But the second important piece about data is that it has multiple interpretations. This is a Sumerian clay tablet, probably around 5,000 years old. The rough translation is that someone owes someone a bunch of barley, like a bunch of barley stalks, and promises to return, like pay off the debt in some like 37 months or something like that. So it's essentially an IOU that's like 5,000 years old. And this was information, right, that was written down so they remember what it is. But when we dig it up 5,000 years later, we don't care about who owes what, whom, because these people are long dead and this IOU will never be repaid. What we care about is that we can take this kind of information and learn something about how these people, like about their agriculture, about their economy. We can have new insights about what this society looked like. And this is something I want you to burn into your brains. It's that when we write a piece of data into our system, we have no idea how it will be interpreted in the future. So when you're building your event sourcing system and you're putting this JSON in some database, I want you to remember that you have to put it in a way in such a way that it will be able to answer the questions you have right now, and also that probably 2 years down the line, your questions will be very different, and you have absolutely no idea what those questions will be, right? And that's why it's important to think about how you're storing, the kind of data you're storing, and to store it in such a way that it will be meaningful in 3 years down the line, when maybe you're not even writing this in Ruby anymore. You're writing this in Java, Scala, or some newfangled language. But it still can read JSON. Because as you noticed on those first 2 slides, I didn't even tell you what format that was. It could have been Eden for all you know. But you were able to interpret it anyways. So those are the interesting properties about data. That's funny, I forgot to start this timer, but I'll figure this out. So, that's data. What about this slide? This is some JSON. This JSON will actually not compile because there's this weird bar thing, right? JSON can't have symbols. So let's pretend it's not JSON. Let's pretend it's Ruby. So at least it will compile. Do we have an idea what foo could possibly represent, just based on this slide? Result of, yeah, you can't do anything. So let me help you out. Let's say that it's actually called total, and the bar is actually calculate total. Do you now have some idea of what this represents? You have some idea, but can you tell me what the result would be? 42? that is the correct answer. That's the secret answer. Yeah, so the problem with this is no longer data, because there's a function in there, and we need to understand in what kind of runtime this function will run. We can, of course, maybe look into the source code, assuming we have access to the source code. Now, this source code, if you look at this, can you guess? If I tell you what the items are, will you be able to tell me what the result would be? It seems reasonable, right, that you would. So these are what we call calculations. Calculations are functions such that the output is dependent only on the input and nothing else. Now, it's not entirely true that you can know what the answer will be, because we're Ruby developers, so maybe someone did something like this, right? But it is a reasonable assumption that we can analyze this code and say, yes, this result will always be the same, and if I run it once or I run it 100 times, it'll always give me the same result. That's the definition of a calculation, that the output is only dependent on the input. And it doesn't matter how many times you run it, you'll always get back the same result. Okay? In the real world, the Enigma machine is a calculation. Because the Enigma machine is this complicated piece of machinery that you feed it two things. You feed it the encrypted message, and you feed it a set of settings. And when you get the result back, the decrypted message, it doesn't matter if you run it once or a million times, you're always going to get back the same result. The Enigma machine might be so complicated that you can't figure out what the message would have been decrypted without actually running the thing. So you need to run it at least once, for example. But whether you run it once or a million times, it's the same result. And the way, for example, you can crack an Enigma machine is instead of trying to crack the algorithm, you just brute force the settings for it, for example, right? Questions so far? Or just, except Nick. Nick, what's your question? Oh, shit, sorry. Oh, wait, sorry, I can't swear. You gave me one of the fizzy. That's not cool. All right. So we're back to the slides. We have the same slide, but this time we introduce the sales tax. Is this still a calculation? It would be reasonable to assume that, yes, this is still a calculation, because why? The output is dependent only on the inputs. I want you to repeat this over and over in your head until it becomes second nature. Now, what if I change the argument list? Is this a calculation? Maybe. Yes, no, I love it. It's both. It's a Schrödinger calculation. It's both a calculation and not a calculation. It depends on what sales tax is. Because if sales tax is, for example, a constant in the class or a global or maybe even in the environment, but you set it once during the runtime, for the purposes of your understanding of what the system does, this is a calculation because it won't change, right? But if the sales tax is an instance variable and anyone can change it at any time, then you can no longer make predictions about what the value is without actually running it at a specific time. Agreed? A more realistic example would be maybe if this was called current user geo sales tax, and then it would be a lot more obvious that, yes, this is no longer a calculation because we're assuming that users come from different geographies, and so this will not always return the same result. So we get to our next name. Sorry, I messed up the slides. That's okay. These things that are not calculations are actions. And as Michał showed yesterday, there's a lot of ways we can think about the coordination between certain things, right? But all of these are examples of actions. And the definition of an action is following. It's a computation that is dependent on either when you run it or how many times you run it. That's all it is. That's all you ever need to understand, is the calculation, output dependent on input, action, it's dependent on when or how many times you run it. So these are all examples of actions. And notice ship items is you have to have a call exactly once semantics, but if you have an idempotent key, order ID, you can have call at least once operation. But you need to call at least once because otherwise the shipment will never get sent, right? So those are actions. In the real world, there's this web service called Hotbits, where I think it's in Fermilab, and they've set up a Geiger-Müller tube hooked up to a computer, and every time you ask the service, give me random bits, it will analyze the tube, and so basically it's dependent on radioactive beta decay. And due to the way that quantum mechanics and physics work, it's completely unpredictable. So it's a true random number generator. And so it's a perfect action because the only way you can get any information is to call it, and every time you call it, you always get a perfectly random bit that can in no way be predicted. So those are our three terms, which actually, this is functional programming. This is the essence of functional programming. The only thing that functional programmers do is that they understand these three things, and they identify these three things in their own system, and then everything else is just sugar. It's more interesting ways of figuring out how to build complex coordination systems between these things, or how to take things out or put things in, but it always comes down to this. And what's amazing about this is that you don't need functional programming, like you don't need to learn a specific language to identify these three things in your own system. But the real question is, why would you want to, right? This talk, it won't teach you everything you need to know about programming. That will take a lifetime of study. But my point is that until you start identifying these three things in your own system, you're going to have a hard time, like moving forward, as it were. One of those properties, one of the first things you can do with this new information that you've just gleaned is tomorrow when you sit down at work and you identify what is a data and a calculation action, you can take I'm going to tell you one quick tip of what you can do with this information, which is this matrix right here. One of the interesting properties about these three things is that they have specific properties of composition. If you take some data and you mix it with more data, you get data back, which means that it's still information at rest. You don't need a computer to interpret it. But as soon as you introduce a calculation, like we introduced the sales tax into our JSON payload, it is no longer data. So it means that anything that is dependent on this piece of thing is now also a calculation. And similarly, if you have an action, then anything that is dependent on the output of this action, since an action is dependent on when or how many times you call it, by definition, everything else that depends on this thing is also now an action because it's also dependent on when and how many times you call it, right? Or another way of thinking this, if you want a more visual, visceral version, is imagine you have a swimming pool and then someone contaminates it on one end. It doesn't matter where they did what they did, you're not going into that swimming pool. And so every time, so this is the side effect you rant, right? This is like the FP people are like, don't do side effects. It's not about side effects. It's about when you do something in the bowels of your system that is dependent on time, on when or how you call it, then everything else that is dependent on a thing automatically also becomes an action, and it's hard to reason about. It's hard to reason about because you are now a big coordination machine, and you sort of have to keep the entire thing in your head and wonder about all the different edge cases. Is that making sense? All right. So let's look at an example, because this is the most important thing, right? The fact that you have data as calculations, actions. But I want to leave you with a little more practical advice of how you can apply this to your daily work. So one thing we can do is let's look at Rails. This is our first visualization. It's a call graph. It essentially shows a dependency between things, right? Because you have a layer. So each of these horizontal things is a layer. So you have a layer of routes. For simplification, I'll just show 2 of each. But you can just imagine there's n. So that we have a route. A route usually is dependent on a controller because it calls the controller. A controller calls a bunch of models, and it calls a view, right? Simple enough? So what happens when you're building this Rails application? Usually the first thing you do, historically, is you start putting more and more logic in the view until you have a couple of thousand lines of a view with a bunch of ifs and all this other stuff, and you realize that this is not manageable. So what do Rails developers do always, historically? Concerns. Concerns do not solve the problem, as we know, but this dependency graph, this call graph, shows why it doesn't solve the problem. Because concerns just take a big blob of code and move it into a bunch of files. But in runtime, it's still just one big dependency, right? It's split across multiple files, so you're sort of hiding the complexity. But in runtime, that same exact complexity is still there. And so the complaints you have about why concerns don't fix anything, this is the reason why. Like, this is a visualization of the problem versus just saying and ranting that concerns don't do anything. So once we realize that this is not the solution, usually the first thing that historically we did is we made decorator objects, right? Let's move a lot of the logic of the view into a separate class. But who creates that class? The controller. So now the controller is doing 2 things. It's creating a decorator class, and it's creating the actual view. And every time the dependency, this call graph, shows that you're pointing an arrow up, that's an indication that something has gone terribly wrong. And in practice, how this ended up is once people started creating all these decorators, they realized that whenever they want to change something in the view logic, they usually had to change two things, both the decorator and the actual view, because they were both dependent on each other. So yes, we moved some code out into a separate layer, but it turns out that the coupling is so strict that you didn't really abstract anything out. You still had two places that you could constantly touch and then keep synchronous. So what else can we do? Well, it turns out that some things you can actually modularize. For example, if we have some kind of date time concept, and you have a library that takes this date time and makes a relative string, like 3 minutes ago, that is a self-contained thing. So if you have a library, for example, that can take a date time and convert it into this kind of humanized string, the call graph shows that this is, in fact, a simplification of your architecture because you were able to modularize and pull out something, and the controller doesn't need to know about it at all. The controller just passes down the date time, and then the view calls it and says, I have this date time, but I'm really interested in this human string. So that is an example of how some things were, in fact, a good way of modularizing Rails code. But there was a lot of code that wasn't able to be modularized in this way, and that's because most of the view code was talking to models, right? You had a bunch of view logic that was iterating and touching models. And again, it took us a while to learn why this was a bad idea, but if we had drawn this call graph, we would have seen right away that this is going to end in disaster. Because again, we have arrows pointing up, okay? So what's the next thing that happens when you have a bunch of views that are talking to a bunch of models? What's the next blog post that people wrote? Move your view logic to where? No, you're skipping a step. To control, in general, there was this movement of move everything from the view into the controller. JavaScript, yeah. CoffeeScript, if anything, at this time. This is like circa 2015. So all the view logic went into the controller. And then, because it was, in fact, simpler, because the controller is already talking to the models, so it did simplify the view part, because the view part no longer has these up arrows. But what happened over time is obviously the controllers grew exponentially big, and when Rails developers looked at it, they went, I was told that functions must be small, so what do? We make concerns. But concerns don't solve the problem, they just hide the problem. So after we went through this entire phase of, okay, so concerns are not the answer, there was an entire bunch of blog posts and conference talks about thin controllers, fat models. So now the controllers are thin, but the models are complicated, because instead of just being simple ORMs that are talking to the database, wrapping the database, they now have all these weird dependencies and coupling, because we moved all the logic there. So in a way, yes, this is better than what we've had previously, but I mean, it's not great, it's still not perfect. And over time, the models grew. So classically, what is the first thing Rails developers do? Concerns. And so now you have a model that's still complicated as it was, but a bunch of logic hidden in a bunch of files, so everyone's happy. And then over time, we realized that, no, this doesn't actually solve the problem. So we have service objects. And service objects, as you can see by this call graph, actually solved a legitimate problem. Because now you can argue what exactly is a service object. Is it a repository? Is it an operation? There can be multiple versions of this world, right? And we're constantly evolving this, right? This is an ongoing discussion of what are the appropriate layers. My point here is, I'm not here to give you the answer of how you're supposed to model your application. I'm here to tell you that you need to start thinking about these layers. Because as Andrzej mentioned yesterday, service objects are not the answer, but that they're the right gateway drug. My suggestion to you is, don't wait until someone tells you what is the next pattern that you should be using in your code. Instead, start drawing these layers and think about which layers make sense in your system, and make sure you don't have things pointing up, and that the layers that you draw, they're legitimate separate abstractions, and not just ways of splitting out code so you have you have like a good score on climate code. By the way, is climate code still a thing? I feel old. How are we with time? Maybe I should speed up. Stratified design. Stratified design is sort of the name behind the thing we're talking about, which is let's think in layers, and let's make sure that the layers make sense. So let's look at a version that's not, application-wide, but let's look at a version of stratified design function or method scoped. So here's a function I took from a blog post, which is essentially, let's find the most unpopular book that was sold, right? I mean, it's not, I don't know if it's pretty Ruby, but it is Ruby that you will see in the wild. There's some iterating, and there's some ifs, and then there's some sorting, and it's not rocket science. So obviously, everyone that sees this code goes, we need to refactor this. Let's extract method, and let's use pattern X, Y, and Z. So you get a version that's more like this, right? We extracted out the isBook because that's a domain-specific knowledge. Maybe we replaced the each with a each with object, and we did a couple nice things, right? I think this is pretty legitimate to say that this would be considered a refactoring process. I would argue this because this is what the author of the blog post essentially said, that this is the improved version. Now, it's true. I do not doubt this because it is a better version, but I suggest that we can do better than this. So here's the original version as a call graph. Notice that there's 2 orange arrows. I don't know about you, but when I'm reading code, there's certain functions, there's certain operations that you get a spidey sensation. When you see hash new or hash set, I'm not saying it's wrong, but you definitely slow down and read deeper because you've been bitten by bugs that are related to state. And you realize that these functions, they're potentially important to understand if there's some edge cases that we need to worry about. Agreed? This is the improved version. We see that there's an additional layer. The isBook is an additional domain layer that we have now. And we changed some functions around, right? We're no longer using each now, we're using each with object and so forth. But as you should be able to see visually, we're not fundamentally changing anything yet. So when I was looking at this code, my first thought was, there's a bunch of code that's essentially what it's doing is it's talking about the semantics of, I want a mapping of items I have in the system to how often they appear. And there's a name for this. It's called frequencies. And so what I can imagine is I'll just write something that's called frequencies that takes this map and generates this map that says, here are the items, and for each of those items, this is the number of times it shows up. It's the exact same code as we saw before. It's just that you hide it away in an abstraction because nobody cares how it's implemented if you give it a name, right? And similarly, now that I have this concept of frequencies map, I can do things like maybe I should add a method called min_value that returns the minimum amount from this map. And what you notice is the call graph changed. There's the isBook, that's a domain layer, separate thing. But then there's this layer that's not quite, it's not exactly a Ruby collection. It has more specific semantics, right? And if I work on this more abstract layer, I no longer have to care about the fact that it uses hash new and hash set and all this other stuff. And notice how all the spidey sense logic went into this one dark corner that if I just verify it once that it works correctly, when I'm reading other pieces of the code, I don't have to worry about it. And if I came up with maybe a better API for that middle layer, I wouldn't have to do that call to first, and then I could draw a hard line and say, I don't have to no longer care about this bottom part. Is it okay if I run over time a little? All right. So obviously, I can't teach you how to design your systems in a 40-minute talk. But I posit to you that if you start looking at the data, the calculations, and the actions in your own system, you start building these call graphs. And I wanted to offer you some simple advice, that things you could actually take home today and apply tomorrow. So the first one is a straightforward implementation. The stratified design says if you build your layers correctly, it will be immediately obvious that there is some complicated thing here that you can simplify. You as Ruby developers are very aware of this because this is all of those blog posts about refactoring and all the patterns for different ways of extracting information. You're already good at this. My suggestion to you is that if you look at it from a call graph perspective, you'll get better at not doing it ad hoc, but doing it systematically. The abstraction barrier is this idea that can you in some way make sure that the layers are so good, they're so well separated that you can draw a fat line and say, I never have to care what's under this part, right? Like, it's completely opaque to me. For example, you all use the things like the Ruby Ruby collection, but you have no idea how they're actually implemented because you don't care. It's a good abstraction. Andrzej gave a talk yesterday, and he made this wonderful fat line between the application and the domain. Intuitively, he created an abstraction barrier without even knowing it, right? And that's how you know you've got good design, when you can do these kinds of things. The minimal interface, once you've got these layers, you need to wonder, are they the right abstraction? Are they the right layers? Apotonik gave a talk on Friday. He accidentally came across minimal interface because he realized that the surface area of reform had too many things going on that could potentially go wrong because there was a coupling. There was examples of coupling that weren't explicit in the API that the users were misusing. And he realized that he could split it into a bunch of separate classes, right? He took one big layer and he split it into separate layers, and then he hid those layers behind like a single call to like create new object of reform presentation that can't do anything except give you various kinds of information about the view part or the validation part. So he applied this pattern of figuring out what are the layers of reform and then creating better layers with a minimal interface. And the last one, this is the most artsy-fartsy in the sense that it's, we don't exactly know what it is, but it's this idea of be comfortable with your layers. If there's too much going on in a single layer, you need to think about how to split it up. But if you go overboard and you create too many layers and there's not enough cohesion between them, that's also not good. So think about your team, think about yourself. Don't create layers just for the heck of it. So if someone comes along like with Trailblazer and says you need to have 20,000 layers, I'm not saying that Trailblazer does, but if Trailblazer or some Failblazer comes along and says you need 20,000 layers, you need to question it always. Similarly, if DHH comes along and says you don't need any layers, you need to question it also, right? You need to find the right amount of layers that you and your team are comfortable right now, and maybe that'll change over time, right? This is this idea of just working towards building better intuition for good design. And this is not something that can be taught, but it's something you can learn over time. And the thing is that these ideas, they're applicable at various levels. So we saw this example of how this will apply to how to structure a Rails app, but it also applies to, for example, on the global scale of how it applies to your microservices. If you figure, a lot of problems that I saw with how microservices are built is when you look at the call graph of these microservices and their coupling, they didn't create good abstractions, good layers. They just split up a bunch of modules into separate web servers and prayed, right? And the same thing can be said for the layers, where sometimes you have the wrong set of layers, and the same thing can be said for functions. And this is the part where I feel Ruby developers are best at because they're used to all these kinds of extract methods and all these kinds of other patterns. But those are just names for specific things, while this is sort of like a universal truth. We're almost there. This is the second visualization I wanted to show you. Imagine you have event sourcing, and you have a shopping cart, and you have this business rule that says, we can't have more than 3 items in a shopping cart for some reason. So you get a command that says add item, and notice there's already 1 item in the shopping cart. So we're processing this new command, and we check the cart. No, it doesn't have more than 3 items, so we update the cart, and we publish an event to the system. Now, if we wrote this in a handler in such a way that we can guarantee that these operations can't happen out of order and they're, for example, inside of a database transaction lock or something, we can simplify this visualization and basically say these three things happen and there's no way to sort of get in between them, right? Simple enough. Now, what happens if the user clicks again? Well, then a second thing happens. So fine, so good. But then business comes along and says, oh, we're publishing these events about items being added. We have this new policy that if you add 2 items to the cart, you get a free gift, right? So between the first publish event to the cart, we realized that we're going to react to the event item added. We check that the items are not, we're not exceeding 3 items in the cart. So then we add the gift, and we publish an event, and then the user clicks again. But this time, when we check the cart, we realize that, oh, we're already at 3 items, so it's not going to fail. We're not going to be in a bad state. It's just that that last item won't actually get added. No harm, no foul. But from what I've heard, this is not how you build event sourcing systems, because this thing would probably be on a separate stream, right? You would have a separate handler processing this information, that information, possibly. And how would that look? That would look more like this. This is more realistic. These are separate workers processing this information separately. And now, this visualization, it doesn't say you have a race condition in your system. But what it does say is that you need to analyze whether you have a race condition in your system, because it's dependent on how these things are actually implemented. So the second visualization, because this is just a sneak peek, is this timeline concept. This timeline concept, similarly to the call graph concept, visualization, it doesn't give you the answers, but it gives you a map of how to think about your system in such a way that you can identify this, right? Because tests will not find this, because this is analyzing your system, not just randomly testing your system. So this is a wonderful visualization that you can apply to your daily work to sort of figure out, are there things that are possibly forking? And if they're forking, are we sure that they're merging back correctly? Okay? So next time someone tells you that functional programming is pure functions without side effects, I hope you're going to set the record straight. Fun fact, if you have a function in your system that calculates something and then puts it in a cache, because you don't want to calculate more than once. But then you have this like try-catch exception, in case your Redis is down. So if like you can't connect to the network or it fails, you'll just recalculate it, and the caller will have no idea that something went wrong. Is that a calculation or an action? If you call it 0, or if you call it 1 time, you call it 10 times, and you get always the same result, is it a calculation or action? Calculation. It doesn't matter if there's I/O. In your specific case, for your specific context, you're saying, I don't care that there's I/O. Sometimes the function takes longer to run, sometimes it takes slower, but in this specific context, I don't care. So in your system, this might be a calculation, but from a purity perspective, there's side effects because there's I/O, right? But remember, we don't care about this definition. We care about the one that makes sense for understanding how our system works. Now think about the alternative case. There's a calculation that is completely dependent only on the input, but it takes really long time to run. It's really CPU intensive. So you want to control when it gets run. It's an action, but from a mathematical perspective, it's a pure function, right? So it doesn't matter what things are pure and what things are side effects. It only matters if which parts of your system, the outputs are only dependent on inputs, and it only matters which things are things such that you care about when or how many times it runs, because those things need to be coordinated. And once something is an action, everything that touches it is also an action. And you're trying to push all those things to the edges of the system, because then a lot of the rest of your system becomes easier to understand. So this is the most important slide that I need you to take out of this presentation. Stratified design is a really useful tool for thinking about how you build your systems. These are all examples of architectures that if you ask me to right now, I could draw how they map to what we just showed, right? Like with the MVC thing. And so, but I don't have slides for all these architectures, but I made one just for Andre, because this is your classic relational database, right? From router to controller to model to DB. Because the DB is side effecting, that means that the models are side effecting, which means the controller is side effecting, which means the whole thing is what? An action, right? And what did Andrzej do yesterday? He showed how, when there's a lot of code in the models and the controller and everything, you can't reason about anything because everything is dependent on time. So he pulled things out, right? He said the models, they should be simple ORM kind of stuff, right? And all the domains, they're not specific to a database. There's no dependency on the database anymore. And then he drew this nice fat line and separated the application part from the domain part. But if instead of drawing a big fat line, he drew circles, he would essentially get the onion architecture, right? It's amazing how simple this idea is, but how far you can apply it. I'm done with my talk, but I really suggest that if anything I said piqued your interest, there's this book called Grokking Simplicity by Eric Normand. The title of this talk is based on this book, and Eric goes into a lot more detail and explains all this stuff that I said, but in a way that actually makes sense. So I highly recommend you go check this book out. It's no coincidence that it was written by a Clojure developer, but it's written in JavaScript, because these ideas, they're timeless, and they're irrespective of what actual programming language you use. So if Eric can show that you can apply all this stuff to JavaScript, I am sure you can find ways to apply this stuff to your Ruby code. That's my talk. Thank you. Nick has a question.
Thank you for this beautiful talk. I'm wondering, in the call diagrams you had, how do you decide what direction an arrow goes? Because I didn't really understand how you can figure out if the view is asking a model or if the model is asking the view. Like, you had this, like when something goes up, there's a problem, but how do you know what's the direction?
I needed to simplify this just because I have a slide. The view layer and the other layers are separate. They're independent. Notice that there's no arrow pointing between the view and the model part. So it's just important to show that they're on separate horizontal lines because they're completely independent of each other.
Yeah, but in a very early slide, you had this. I think when you were talking about decorators.
This one?
Yes.
Okay.
So how do you know the yellow or orange arrows go up? Like, what would the code look like so you know something is pointing the wrong direction?
So when you think about it, if the layers were reversed and the views were on top, right? Mm-hmm. Then the arrow, there's one arrow from the controller to the view, and then the models would have this situation where it's a little mind-bending, but if you switch it, you'll get back the same result.
Is mind-bending, of course.
If you switch, it turns out that it's irrelevant, because if you switch layers, you're still going to get arrows that are pointing in the wrong direction.
Okay, but is the view changing state or something?
Yeah, in this specific case, I was talking about how you sometimes have these views that are iterating over models, yeah. Right? Not even necessarily changing the models, right? But they have a dependency on the model. So like that you're doing users.each, and then inside you're doing a bunch of data.
Okay, but that's so basically the view knows too much about the model.
The view knows too much about the model, exactly.
Okay, I see. Yeah, I've seen those kind of views. Thank you.
When you've mentioned that frequency thing, although that the whole talk was heavily backed up by functional programming, I got a notion that and please correct me here if I'm right or wrong, you suggest that if we have some fishy piece of code, that we should do something like come up with the method name or a message that we should be thinking in terms of, rather than having that hash something. It resembles to me something advocated by OOP design, that you're not having method calls because you have objects or classes, but you have those classes or objects and then the layers because you want to do a particular thing. Was that what you were trying to...
I'm having trouble parsing your question. But that's probably me, not you.
Okay. Sorry. So maybe could you go back to the code with the
sure.
frequencies? Could you elaborate on the how you come up with the frequencies part?
Okay, perfect. So item sold filter returns a new array of things, right? Now, I did dot frequencies because I know how Ruby developers like to chain their things. If I was to write this code, I would probably just write a frequencies function that took the array as its argument and returned a new thing. That new thing, you can think of it semantically as a subset of a hash map. You can implement it as a hash map, but you don't give it the entire API surface of a hash map. Instead, you give it an API surface that this represents semantically something that has a key value association of item to count. And so you can imagine we could write like a if we implemented it this way, we would have implemented it we would have added a new frequencies method to the array, like active support would do, right? But we could have also done it in such a way that frequencies, or if you called it as a function, would have returned a new kind of class. That new class could be called a frequency map. And the frequency map would just have the semantics of being able to, for example, return min value, max value, and nothing else. So it's a question of, can you identify, so every time you make something less abstract and more concrete, you're reducing the amount of the surface API. So fundamentally, you're making the class weaker. You're giving it less features. It can do less things, but because it can do less things, the things it can do, it's more cohesive. So instead of just having a hash map that can do everything, you have now a frequency map, and the definition of a frequency map is it's a mapping of item to some kind of frequency count, and that's all it can do, right?
Okay.
Does that make sense?
Yep. Thanks.
Okay. All right. I think we're done. Thank you.